All right, as we continue down this logging road, it's a bumpy logging road. We see that there's still some logging to do. I'll save the puns and double meanings for another lesson, but maybe you are wondering why the name logarithms? Just what is that? And I'll be honest, I don't have a real good answer exactly where that came from mathematically. But remember, a logarithm is an exponent. And today what we're going to do is we're going to talk about properties of logarithms. So wouldn't it make sense to say, well, geez, if a logarithm is an exponent, then this would be like the same thing as properties of exponents. Well, actually, there is some truth to that. In fact, just like we've learned, and it's a very familiar property, I hope, that if you're in a situation where you're multiplying, that you add the exponents, you're going to find out with logarithms that it's the same. You're going to find out that if we're adding logarithms, that meant it was a multiplication problem. And just like I hope that we've come to know that if we're in a situation where we are dividing, that we subtract the exponents, it's going to be the same with logarithms. You're going to find out that if we're doing a subtraction problem, then that would have come from division of logs. So properties of logarithms, well, yeah, but they are actually the same as properties of exponents. And so take a look at your guided notes paper to help us think about some properties that actually, before I even show you, just to kind of get us to think about some properties, we have a problem that's kind of interesting, 2 times the log base 2 of 8. Now, if we were going to do this problem by thinking like a log, which is kind of neat to do, you would just simply ask yourself, well, what is the log base 2 of 8? Now remember, that's the exponent that you would put on this 2 to get the number 8. And so the exponent that you put on 2 to get the number 8 is 3. So now we're trying to figure out what would be the value of 2 times 3. And, well, of course, the value of 2 times 3 is 6. So could we get the number 6 by using properties? Well, yes, we can. I just haven't shown you the properties yet, but I want to tell you that it actually is going to be the case that when you're multiplying, that would have been the same as changing that multiplier, that coefficient, to be an exponent. And so I'm actually able to change that 2 to be an exponent on 8. Now that gives me 8 squared. Specifically, it gives me the log base 2 of 8 squared, and of course 8 squared is 64. Now, what is the log base 2 of 64? Well, that's like asking 2 to what power equals 64. 2 to what power? Well, 2 to the third power. Oops, 2 to the, to the 6th power. So, yeah, it comes out to be the same answer. And so the whole point here is that we're going to have properties that I'm going to teach you that are going to help us to do new problems, and they work. They definitely are true properties that will give us the same answer. Now, there's 3 of them. There's a power property. The power property says that if you have a number out front, it's a coefficient, that it's able to come up as an exponent. Some people like to draw that arrow that I drew. And so we end up now with a new statement. We end up with the log base b of m to the p. That's called the power property. Now, I have that one in the middle because that's like the most popular property. That's a property that you will use in 2 scenarios. One of the scenarios that you'll use it in is when we're doing a product. Now, the product property says that if you're adding logs, that's going to be the same as a multiplication problem, the multiplication of m times n. Now, I want you to see what happened here, because not only did we change a plus sign to become a multiplication sign, but we've also taken 2 logs and we've condensed them together to be 1 log. And so this is also part of the property of when adding logs, you multiply. Now, we call this condensing because condensing is when you take multiple logs, in the case of this problem 3 logs, and you condense them together to be 1 log. By the way, we have a small typo here. This is supposed to say the log base 3, not the log base b. It's supposed to say the log base 3. In any case, if you have 3 logs, you can condense them together to be 1 log. Now, I like to encourage students just to write 1 log so that you're guaranteed now to condense this to be the multiplication of 8, 4, and 2. the multiplication of 8, 4, and 2, well, that ends up being the number 64. So we end up here with the log base 3 of 64. And so we have used the product property to condense this together to be 1 log of that multiplication. You want to take a look at another one? Okay, now what we have here first are coefficients, and what you guys are going to grow to know is that coefficients always have to come up to be exponents. When they come up to be exponents, we now end up with some new values. We're going to end up with a 5 squared. We're going to end up with a x cubed. But you always bring coefficients up to be exponents first. Now that I do that, I'm able to recognize that when you have an addition problem, you're able to condense it to be 1 log. And as I've said before, I encourage you to write 1 log so that you're forced to condense this to now be 5 squared, which by the way is 25 times x cubed. And so we get the log of 25x cubed. Condensing is taking multiple logs and pulling them together to be 1 log. And maybe you want to try this problem on your own. I encourage you to think what you've seen so far to see if you can condense this together to be 1 log. Now, if you're trying to do it on your own, the first thing you should be doing is bringing that coefficient up as an exponent. Now, when you bring it up as an exponent, you'll now have 2 to the 3rd power. 2 to the 3rd power is actually another number, right? It's the number 8. And you'll be able to show that when you take this addition problem and you condense it together to be 1 log. It's going to be 1 log of the product. It's going to be the product of 4 times 8. Now, that's 32, but what we really have here is the log base 2 of 32. There are going to be some problems where, because of the numbers that are given, that you're actually able to calculate the final value. What do I mean calculate? Remember from yesterday, 2 to what power equals 32? Yeah, you're actually able to calculate that to be the number 5. And so we're able to take this logarithm problem and we're able to actually simplify it the whole way down to be 1 final number, the number 5. That's the product property. The product property says when adding, you can multiply. So we have its partner. We have the quotient property. It says when subtracting, you divide. Now take a look at how you're dividing. The simple story is whatever is being subtracted, and in this case, it's the log of n that's being subtracted. Well, that always ends up in the denominator. So again, whatever's being subtracted ends up in the denominator. So we can take this log base 3 of 10 minus log base 3 of 4, and we can condense it to be 1 log. Now, we condense it to be 1 log that's going to end up being a division problem. It's a division problem because this one is subtraction. So it's real simple. Whatever's being subtracted in this case is the 4, is going to end up in the denominator. And honestly, whatever's being added, it is actually true that there is a plus sign on this log of 10, so whatever's being added ends up in the numerator. Now, 10 over 4 is able to be simplified, as you could always simplify that to be 5 over 2. But in the end, we end up with the log base 3 of 5 over 2. How about if we have multiple logs that are being subtracted? Well, as I said, whatever's being subtracted is going to end up in the denominator. Whatever's being added is going to end up in the numerator. So write yourself 1 log. Make sure that you write 1 log of 1 fraction. Now remember, whatever's being subtracted ends up in the denominator. So that means we're going to end up with 6 and y in the denominator. But whatever was being added, that is this x, is going to end up in the numerator. So again, we have ourselves the log of x over 6y. Do you want to try one? It might be this problem that you want to try. If you are trying it, you always have to bring coefficients up as exponents. It's kind of like a preliminary step. Now, right, you would get 2 to the 4th power. Nothing else has changed yet. Now, 2 to the 4th power is 16. 2 to the 4th power is 16. We also have a subtraction sign, so we're going to be able to write this as 1 log of 1 fraction. Whenever you see subtraction, you make a fraction. Now, that blue 2 to the 4th, that's equal to 16. The black 16, this black 16 here, that's going to be the one that we divide. Interesting, we actually are dividing two numbers that are the same. Now, you know that when you divide those, you're going to get the number 1. But the interesting thing here is that this is like asking yourself 5 to what power equals 1? Wait a minute, 5 to what power equals 1? Well, that's always going to be 0. So it looks like this problem was able to simplify all the way down to just the number 0. Now, we can combine some properties. Basically, it's just the problems get a little bit bigger. So if we want to combine some properties here for number 7, yes, we see lots of addition and subtraction. One thing I want you to realize here is that when you have a mixture of addition and subtraction, all you're going to end up with is putting your answer into the correct place of the fraction, okay? Because all this is going to get condensed together to be 1 fraction. In the numerator is where we put the addition numbers. So 3 goes in the numerator, 16 goes in the numerator. Now, when they go in the numerator, you're going to multiply them together. That's the only correct way to kind of combine them. Now, whatever's being subtracted goes in the denominator. So the 2 goes in the denominator and the 4 goes in the denominator. But again, you have to combine them by multiplying. So we end up with, what? 48 over 8. Now, 48 over 8, that's actually the same as 6. So really, we end up here with the log base 4 of 6. Now, we kind of have to ask ourselves, can we figure that out? Can 4 to what power equals 6? No, we can't. The numbers aren't such that we can come up with an exact value for that. So we leave the answer as the log base 4 of 6. What if we have some fractions? Okay, sometimes when students see fractions, they start to get a little scared or think that, you can't do it. But there's no reason you can't bring these coefficients up as exponents. That's what we've done now a number of times, and it still works that way. So we have an exponent of a half, and I guess we end up with an exponent of 5 halves. Now, there's something I need to show you here, and it's just to help you continue to grow in your understanding of logarithms. You see, if I have an exponent that has a denominator, and in this case, both denominators are the same, I would be able to write those as radicals or roots. Remember, a 1/2, specifically a denominator of 2, that's the same as a square root. And remember, a 5 halves. Well, a 5 halves is going to be the same as having a power of 5, but having a square root. And so I'm able to write both of these as square roots, because now what I can do is I can condense these with a plus sign. Remember, when you have a plus sign, you're able to condense them together by multiplying. And so I'm going to multiply my 2 square roots. Now, how do you multiply square roots? Well, the answer is simple. You are allowed to get underneath there, and you're allowed to multiply the 2 and the x to the 5th. So I end up with the log of the square root of 2x to the 5th. Now, that was a little tricky. But again, I say to you, if you have a fraction and the fraction has a denominator, that denominator is able to become a root. And in this case, we were able to create square roots that we could combine together into one final answer. Now, could we do the properties backwards? Could we do the properties backwards? Could we pull apart a logarithm? Well, the answer quite simply is yes. But what you have to do is you have to think backwards. You have to think, wait a minute, I could take this exponent and I could actually bring it back down. Wait a minute, I could take a multiplication problem and I could pull it apart to be an addition problem. And same thing over here. I could take a fraction, and I could take whatever's in the denominator and make that be a subtraction, and whatever's in the numerator, I could make that be the addition. So we basically can take these properties and we can think about them from right to left. We can think about doing them backwards. You want to see how it works with this log down here? Okay, now this log down here has got 3 components to it. It's got an a squared, it's got a b, and it's got a c. What I want to help you see is how we can pull this all apart in one step by recognizing, first of all, that we have something that's being divided. Now, whatever's being divided becomes part of a subtraction. What's the subtraction? It's going to be the subtraction of the log base 2 of c. Now, whatever's in the numerator is going to be part of an addition. What addition? Well, I'm going to be adding the log base 2 of b. Okay, so that was the b that I took care of. And I'm going to be adding the log of a squared. But here's the thing, that a squared, that square, it really wants to park itself down here. And so if you're really on the ball here, you would say, all right, I'm going to take that square and I'm going to put it out front right away. So we end up with we end up with 2 addition problems. We end up adding 2 log a and adding log of b. And we end up with 1 subtraction problem, and that subtraction problem is minus the log base 2 of c. So if we want to expand a logarithm, well, that's going to require us to reverse or a reversing of the properties that are on the front of the page. Now, reversing the properties means that we're going to be writing out multiple logs because we're going to be expanding the problem. So what you want to recognize is that the amount of terms that you have, in this case an x squared and a b, is going to dictate the amount of logs that you have. And I like to encourage kids to just recognize that this problem, because it's multiplication, is going to become addition. So there's going to be the addition of 2 logs here. The only question is, what are we going to do the log of? Well, we're going to do the log of b, and we're going to do the log of a squared. Now, as I did on the front of the paper, if you'd like to save yourself a little bit of time, you know that that square is going to end up out front anyway. So anytime you see an exponent, you can even write that as a coefficient, and you got yourself your final answer. 2 log of a plus log of b. Now, you look at number 10 here and you say, well, Miss Naylor, what am I going to expand? There's only one thing. This takes you to the next level of thinking, where you want to recognize that you can think of the number 20 as 2 numbers. Is there any reason I can't think of the number 20 as 5 times 4? Is there any reason I can't think of it as something that's being multiplied that I can now write as 2 logs that are being added? And of course, the only question is, what do I want to add? Well, I'd want to add a 5 and a 4. So I've got the log of 5 plus the log of 4. Now, you ready? Interesting. You can think of the number 4 as 2 numbers, right? You can think of it as 2 times 2. And so that means that I actually could expand this into 2 more logs, namely the log of 2 plus the log of 2, so that ultimately this problem can be thought of as 3 logs that are being added together. What we've actually done is we've factored the number 20 down to its prime factors. And so if you're saying, well, how do I know when I'm done? You're done when you've expanded it down to its lowest and prime factors. Here's a problem that clearly has division. And so whenever there's a division or a fraction, there's always going to be subtraction. Aren't there also 3 terms here? So if there's 3 terms, we know that we're going to have 3 logs. What I like to encourage students to do is to write out 3 logs. Now, maybe you don't like what I'm doing here. Maybe you don't like how I'm kind of creating part of the answer. But I just want you to see that the two items that are in the numerator are going to be my added logs. My one item in the denominator is going to be my subtracted logs. And so all I got to do now is just fill in the different parts. I can fill in a 4. I can fill in an x squared. But are you ready to take that 2 and bring it out front? So I can put a 2 out front, and I can just put an x here. And I'm ready to fill in my 8. So whatever's in the numerator is the added, and whatever's in the denominator is the subtracted. And I've expanded this into 3 logs. Now, if you're really on the ball here, you would say, Ms. Naylor, you could actually break this down again. Right, I can think of the number 4 as 2 times 2. So that means that I actually could split this up to be the log of 2 plus the log of 2. So I can split that up a little bit. Now, this 2x, 2 log of x, that doesn't get split up anymore. But the number 8, that actually can be split up. That can be split up into 2 times 2 times 2. Now, here's the thing. You want to recognize that that means you're going to be writing out the log, a minus log of 2 3 times. And yes, you have to write minus because each one of those was part of the denominator. That's getting a little bit beyond what I'm going to expect you to do. I definitely expect you to be able to split this thing up into 3 logs. If you recognize that you can break it down even more, I'm not going to stop you from doing it because it is fully the correct answer. So we get to the point where we can combine, honestly, properties with just some wits. And wits is just kind of my funny way of saying understanding what is a logarithm. And so some of these ideas go back to yesterday, some of them we use today, and you can kind of combine them together. Meaning if you see an exponent, yes, you're allowed to bring that out front. Now, you also might see that you can actually figure out 2 to what power equals 16. So yeah, I can actually figure out the value of this log to be 4, which means that now I'm looking at 3 times 4, which we all know is, of course, the number 12. How about taking something that we did yesterday and using it entirely today? Why couldn't I look at this log of 100 as a common log, that is a base 10, and ask myself that same question, 10 to what power? 10 to what power equals 100 to the 0.1 power? And now I've got myself a situation where we can match the bases. We talked yesterday that I can make this be a base 10. That is, I can make 100 look like 10 squared. And now I can say that my exponents have to be the same. We know that x would have to be the same as these 2 exponents. Of course, you multiply those exponents, which is why we end up with 0.2. Now, what I did there was I used a method entirely from yesterday, which was, again, matching the bases. And here I have a subtraction problem. So if I have subtraction, I'm allowed to make a fraction as long as I put the subtracted number in the denominator. So 128 goes in the bottom, 32 goes in the top. Now, 32 over 128, if you think a little bit about reducing, actually reduces nicely just to be 1/4. So now what do we do? Well, what we have to do is we have to understand that since this 2 is being raised to a power that is an unknown power, it's going to equal 1/4, and 1/4 is the same as 1 over 2 squared, and I'm getting myself closer and closer to making the bases the same. I'm getting myself closer and closer to be able to say 2 to the negative 2. And of course, if 2 to the x is equal to 2 to the negative 2, then x has to equal negative 2. In other words, we made our bases match. Now, there's nothing wrong with what I did right there, but to be quite honest, it was a little bit more complicated than just doing the problem to begin with. Because 2 to what power is 32, actually has a number. It's the number 5. And 2 to what power is 128? Well, that has a number also. That's the number 7. So look, it's just 5 minus 7. Well, geez, 5 minus 7 is equal to negative 2, the same answer that I got down here using properties. I wanted to end the lesson by just going over 2 common mistakes, ones that I wasn't able to really bring up in the examples, but often students will ask about. Now, this first one here, we see that we're subtracting 2 logs, and students will say, well, I know subtraction means fraction, but the problem I see is that students make too much fraction, and that is that they actually will take the log of 10 and divide it by the log of 5. Okay, now, if you're saying, well, what's wrong with that? Well, remember, when you have subtraction, you make a fraction, but it's supposed to be 1 log of 1 fraction. So you kind of have to force yourself to write this as the log of 10 divided by 5, which is actually a completely different situation, as that actually simplifies to be the log of 2. And we want to recognize that what was written over here, when I tried to write the log divided by the log, is a completely different idea than just having the log of 2. And then it's kind of the same idea. A student says, okay, if I have multiplication, I know that's supposed to become addition, but we accidentally tried to create an addition problem where maybe we just say 2 plus 3. And what happened here is all of a sudden 2 times 3 just became 2 plus 3. That's not what you meant. You meant the log of 2 plus the log of 3. And so the idea here is that you have to change it to the addition of 2 logs, not just the addition of 2 and 3. And then the last thing is I'll have students say, well, Mr. Miller, what about the base? You haven't really talked about the base. Here the base was 3. Here the base wasn't shown, but we know it's assumed to be a 10. Here's the bottom line. The base does not really affect these properties. It just needs to be the same. So as long as my base were both 3s, then I can do the property. Here the base is not shown, but we know it's 10, but it doesn't affect my ability to be able to do the property of splitting it apart. So I guess I would say don't worry about the base, but it does need to be the same if we're going to apply any of these rules. All right, well, you're ready to do your homework, and I'm going to provide a selective answer video to help allow you guys to be able to kind of listen one more time and to be able to check some of your answers in the homework.